And now we go to our next talk by Quench. And we selected slightly similar topics for a seminar, so we should hear something in similar field.
So yes, could you see my screen? So thanks very much. Thanks very much for having me. I'm Quench, currently a joint postdoc in Columbia and Flatiron Institute. So the thanks are here for establishing that cosmic ray should be a very important physics in a dwarf galaxies. And yeah, so I'm going to switch gear to a more massive galaxies and hope in the end of this talk I'll convince you that cosmic ray in the aspect of AGN jet instead of the supernova will still playing a major role possibly playing a major role in the massive galaxy. So I'm going to talk about which AGN jet quench star formation in a massive galaxy in this talk. So most of this talk is part of a paper we published a few months ago. So first, a few words about the cooling flow problem. This is a problem for the massive galaxies that we're trying to tackle with AGN jet. And yeah, so for the galaxies, there's much larger L-star galaxy in cluster, we observe strong extra luminosity, and this will imply strong cooling flow. Given such strong cooling flow, we might expect that there's a lot of low energy or cold gas in the core region of the galaxy. However, we didn't find as much a sufficient amount of cold gas. So perhaps all those cold gas formed stars usually pretty high star formation rate. However, this massive galaxy or cluster elliptical are typically quenched and there's no significant star formation. So this all tie in the picture that it must be some sort of heat source or pressure support that will compensate the cooling flow in this massive system and could solve the cooling flow problems. So in the simulations, the cooling flow problem will typically present as very high star formation rate. So as you can see, these are 10 to the 14 solar mass, halo mass simulations that suffering from a cooling flow problem. At redshift 0, the star formation rate is order of magnitude too high. Yeah. So in this work, we're trying to try to see whether any of the AGN jet model, which we see in this massive system, that could possibly quench the galaxy and solve the cooling flow problems. And yeah, and if any of them work, would that have anything to do with like inducing turbulence or injecting cosmic ray in the CGM intercrustal medium? And this is also part of work that we established like in the previous years that we say that injecting turbulence and steering out turbulence and injecting cosmic ray could potentially be a very important aspect of AGN feedback. Will possibly more stably quench the star formation and cooling flow in this massive galaxy. So we test a wide variety of AGN jet model in this work, mostly in 10 to the 14 isolated galaxy simulations. We do have a few other halo mass range, but in the subsequent work, but yeah, most of the talk I'll be talking about will be 10 to the 14 isolated galaxies. We systematically varies the AGN jet. So these runs are run with AGN jet with constant flux, but we varies the energy composition, like in the thermal, kinetic, magnetic, or cosmic ray energy, and also things like duty cycle, AGN jet opening angle, and jet precessing, and so on and so forth. So we are running the jet on top of fire stellar feedback, and also other free microphysics, and potentially help us capture the interplay between jet and this other physics and potentially launch the jet in a more realistic environment. Also, we are using super Lagrangian refinement, so which means by merging and splitting particles, we're enforcing higher resolutions around the jet and around the black hole. Yeah. And finally, we're using particle spawning to represent the jet, which means that in the simulations, we spawn gas particles element from the black hole and to represent to catch the effect of the jet. And this gives us a better control of the open angle and also the energy composition of the jet. So this is the whole suite of runs, again, a long list of runs that we've run in this work. And so I will talk about them in more detail later, but more or less we have like a few kinetic jet, thermal jet, cosmic ray jet, and those experimenting different magnetic field composition. And for all of these different categories, we test things like different energy flux, mass flux, magnetic field, jet width, jet precession, and like specific energy and mass flux and duty cycle, and so on and so forth. So actually, to first summarize what we found in this work is that we found a few criteria for a jet model to be more successful. It is at least in this more 10 to 14 system. And yeah, and this all tied into the picture, to the cartoon picture that we made. So as the jet launch and propagate, it will it will have a associated with a pressurized region, which we call it jet cocoon, and that cocoon will continuously expand, and you will suppress the cooling flow wherever it reach, and we eventually reach the cooling radius, which is a radius within which the cooling flow is strong, and beyond that radius, the cooling time of the gas will be too long to be relevant. Yeah. So the property of the inflated jet cocoon at a cooling radius will be very important aspect of whether an AGN jet model would possibly quench the galaxy and solve the cooling flow problem or not. So one criteria is definitely the energy criteria. The AGN jet should definitely at least have a moderate energy that is comparable to the free fall energy at a cooling radius. So yeah, but it should not be too high. So if the energy is too high, that it will decouple all the gas at a cooling radius, the effect will be very explosive, as you can imagine. Another important criteria is that the cooling time within the jet cocoon have to be long enough. So the cooling time of the jet cocoon have to be much larger than the expansion time of the jet. Otherwise, you can imagine a limit that the most of the energy will be radiated away before the jet cocoon even reach the cooling radius, and it will not have a huge effect to the bulk cooling flow. So this could either be reached by like the thermal or kinetic jet with very high specific energy. You can imagine that with this high specific energy, it will just heat up this jet cocoon to higher temperature, or shock heat this jet cocoon to higher temperature. Another possibility is that the majority of the energy in the jet cocoon is in the cosmic ray form, and that is another form that doesn't radiate away as efficiently. Yeah. So another criteria we found is that the jet cocoon have to be wide enough at a cooling radius. Otherwise, it will just punch a hole through the cooling radius and will not like overall suppress the cooling flow over a wide open angle. So yeah, so at least at the cooling radius, the width of the jet cocoon and the length of the jet cocoon have to be of order unity. So this could again have a few possibilities that could satisfy this constraint. One is that the jet should have a large non-kinetic component, either in thermal or cosmic ray form, or if it's a pure kinetic jet, it would be very fast and very light. Another possibility is that we initially just launch the jet with a wider open angle or make it precess with a wider angle. So, consistently with these criteria, we found a few more successful models that would be stably quench the galaxy. One is a cosmic ray jet model. So these are the cosmic ray jet model, a movie of them in lower energy and higher energy flux end. Also, that if it's a thermal jet, as we said, it needs to be a very high temperature thermal jet, a very high specific energy one. So you could heat a cocoon to a sufficiently high temperature. So this is a thermal jet case. And also there's possibly like a very fast kinetic jet, wide precessing kinetic jet, and the wide open angle kinetic jet category. So this is an example that we have with a wide precessing kinetic jet. It's a 45-degree initial precessing of the kinetic jet. Yeah. So I'll talk a bit more detail in each one of them. So first, going into kinetic jet. So for the kinetic jet, immediate thing we found is that the kinetic jet was associated with very narrow cocoon will always be very inefficient. So this is a star formation rate of a few run that we run with kinetic jet. The black line is the run with no jet at all, and the other 3 runs are the run with different energy flux, range from a few times to 42 ergs per second to a few times to 44 ergs per second. So these are narrow kinetic jet with different energy flux. As you can see, if you are injecting more energy but not like make the jet cocoon much wider, it not necessarily quench more efficiently. As you can see, none of the run is quenched. So if you see the morphological plot in the entropy profile and the radial velocity profile, so this is radial velocity, the black is outflowing, the red is inflowing in both the low energy flux kinetic jet and high energy flux kinetic jet case. So you can see this roughly quantify how wide the jet cocoon is, since it's separate between the inflowing and outflowing. And as you see, if you're injecting more energy, but which not necessarily make the jet cocoon much wider and will not necessarily make more efficient, even if you inject like 2 orders of magnitude more higher energy. On the other hand, if you find a way to make the jet cocoon much wider, you could potentially have a larger effect. So this is an example that we made the jet initially have a wider jet cocoon, or like we make the jet still make it narrow, but just precess the cocoon with like a 10 million year or 100 million year period. So in all of the case, you can see that from up to down, more or less it's an increase of either the open angle of the jet or the precessing angle of the jet. You can see the wider with the same energy flux, the wider either the open angle or the precessing angle is, the more effectively it suppresses the star formation, as you can see here. Yeah, so you will quench the galaxy. Another interesting we found is that the longer precession period also helps. So if it's just a wider jet, you need more or less an isotropic injection to have a sufficient effect at this energy flux. On the other hand, if you have like like 10 million years or even 100 million years jet precession, although it's a narrow jet, you can precess it with different precessing angle, and you can see that it started to have a larger effect in 45 or 30 degree. Yeah. So what we found is that it seems that if you have like a sufficiently long precessing period, the jet will stay in one direction for sufficiently long time for the energy to propagate to larger radius. And actually you can see here. So this is the density profile and entropy profile of the run with just either we just increase the jet width, or like we make the jet precess with 10 million years or 100 million years. So if you just increase the jet width or just have a shorter precession period, as you can see from the entropy profile, the density profile, a lot of energy is kept at the core region of the galaxy. It shock heat the core region of the galaxy more, you can see a much more heated core in either the wide case or the short precession period case. However, if you have a long enough precession period, which roughly like 100 million years, then a lot of energy doesn't just stay at the core region of the galaxy. It's a more smoother entropy profile that is more agrees with observational constraint, and also that you can see that from the velocity profile of the hot gas in the CGN, that it also boosts the velocity at a few 10 kilopascal by at least a factor of 2. So yeah, so it's more effective, and also it's more stable, since that you distribute energy to a larger radius instead of just shock heating the core region of the galaxy. So then we go to the cosmic ray and thermal jets. So immediately we found is that a cosmic ray jet with the same energy flux, the cosmic ray jet are always much more efficient than a thermal jet. So again, this is a star formation rate for the 10 to the 14 isolated galaxy simulations. And the blue and the lime lines are the thermal jet. The green and the blue and the cyan lines are the thermal jet, and the green and the lime lines are the cosmic ray jets. So the upper two are the lower energy flux case, and the lower two are the higher energy flux case. So in either the case, you can immediately find that with the same energy flux, the cosmic ray always quench the galaxy or suppress the cooling for a star formation much more efficiently than the thermal jet with the same energy flux. And this actually holds true even in our current ongoing work, that where we test that a 10 to the 12 or 10 to the 15 solar mass. So in all of the case, with the same energy flux, the cosmic ray will always quench more efficiently. So there's a few things that we think this is why this is the case. The first thing is that a cosmic ray will provide extra pressure gradient, which is another pressure support. So here we try to quantify the effect. The blue line here is the accelerations created by the cosmic ray pressure gradient. And to compare them with the gravitational acceleration, which is the black line, or the gravitational subtracted by the rotational support, which is the gray line. As you can see for the cosmic ray case, which is the right-hand side, the cosmic ray pressure gradient will always be comparable to the gravitational accelerations at the core region of the galaxy, like a few 10 kilopascal, which the cooling flow is strong. On the other hand, for the thermal jet, since in this radius, the cooling time is short, the thermal pressure gradient is not always pointing outward, so you lose the thermal pressure support. So this is, we think, partially why that the cosmic ray jet with the same energy flux, cosmic ray jet quench the galaxy more efficiently. Another very interesting thing we found that also consistent with other found is that the cosmic ray jet change the thermal instability of the CGN. So again, we plot the cosmic ray jet and thermal jet in the temperature versus density and entropy versus total pressure, like the phase diagram. So this is total pressure, means thermal plus cosmic ray pressure. As you can see, since there's an extra pressure, so the gas could actually cool down while maintaining roughly the same total pressure, and this will render a much narrower density contrast as the gas cools down, and this suppresses the thermal instability. On the other hand, for the thermal jet, the density goes to much higher, and that makes the cooling much more efficient in this radius. Yeah, another interesting we found is that in certain limit, the cosmic ray jet will also be less overheated in the thermal jet. So, for example, this is two runs with cosmic ray and thermal jet, both with high specific energy. As you can see, although they have more or less the similar star formation history, you can see that from the density and entropy plot that the cosmic ray jet are less overheated in the core region of the galaxy. Density is also not as suppressed in the core region of the galaxy. We think partially this is because of the cosmic ray diffuse, and they will smooth out the distribution and wouldn't just keep the energy all in the core region of the galaxy and become explosive. So overall, it seems that the cosmic ray require less fine-tuning, is more effective in the low energy case, and also is less overheated in the higher specific energy case. So I'll put a summary here. So we found a few criteria for the jet model to be more successful. One is energy criteria. It has to be high enough, at least comparable to the free-fall energy at the cooling radius. And the jet cocoon has to have long enough cooling time, and also it has to be quasi-isotropic at a cooling radius. Associated with these, we found that the cosmic ray jet will be very effective. Also, if the thermal jet need to be very high specific energy, like a few 10⁹ Kelvin, or like the widely precessing kinetic jet, also possibly stably quench the galaxy. And among these rounds, it seems that the cosmic ray jet will allow the widest parameter space, require less fine-tuning, since that is more effective in the low energy end due to the pressure support and change of thermal instability, and also it's possibly less overheated in higher specific energy. So yeah, I'll leave the summary here and take any questions. Thanks very much.
Thank you very much. So I see applauses, and now it's time for questions. Yes, please, Avedi.
Kunying, that was an interesting possible solution to this old problem. I do have some questions. Well, I have lots of questions, but I'll just restrict it to one or two, if I might. One is that a difficulty of using any kind of feedback in the cooling flows is a balancing problem, right? That you have to have, let's take cosmic rays, that the cosmic rays have to suppress the cooling flow, but not turn the flow off in the sense that you get a reverse flow.
Yes.
Can you comment on how fine-tuned the solution is to actually balance the cooling flow, but not shut it off completely?
Yes. So I think that's part of the reason why I think cosmic ray might be a more preferred solution, since that it actually allows a wider parameter space. So if it's thermal jet, it actually is much more fine-tuned. For the cosmic ray, it seems that, at least for the mass range we survey, it seems that due to the pressure support and the change of thermal instability, it can start to have a larger effect when the energy flux is not as high. And also, it can potentially be less overheated due to the diffusion and the cosmic ray energy transport at a higher energy end. So we actually found a wider parameter space that could work for the cosmic ray than the other possibilities. Yeah. So
and you comment that it helps also in suppressing thermal instabilities, but if the pressure is coming from cosmic rays, is not the density in the cocoon, is it lower than the outside where the gas is still trying to cool? Do you have a problem with Rayleigh-Jeans instabilities?
Yeah. So when we see the density profile, definitely in the cocoon is more pressurized, either with cosmic ray or thermal plasma. So, but we still check for the run with cosmic ray, the density. And so, for example, these are a few runs with density and the entropy profile. I think that at least is to the zeroth order for the hot gas is still reasonable compared with the observational constraint, that the density profile and the entropy profile. That yeah. So yeah, definitely. So yeah.
It doesn't become buoyantly unstable.
Yeah, so it's still like marginally. So yeah, so you can see that the overall the we lay on the back is the more or less the observational constraint, and still possibly within the reasonable range compared with observations. Definitely that we're also working on like a multi-phase observational like plot and try to further narrow down whether any of these model will be more promising than the others. But yeah, to the zeroth order, the hot for the X-ray properties of these hot gas, it seems that it's still at least at the reasonable range. It's not, yeah.
Okay, all right, thank you.
So do we have more questions? Yes, please, Sergio. Unmute yourself.
Sorry, I was looking for the button to raise my hand, but I couldn't find it. This is super interesting work, Quench. I was wondering, so when you inject cosmic rays with AGN,
Yes.
Is there any observational constraint or any idea, like, do we have any idea of what is the fraction of cosmic rays you can inject? Do we have any idea of, like...
Yes, that's part of things. So ideally that the best way to do might be like do a shock finding of the CGM and inject the cosmic ray there. But again, so for those cosmic ray jet here, I'm just injecting most of the energy in the cosmic ray. Ideally, I would definitely also like try, for example, like as you do in the supernova, that perhaps like 10% or a few percent of the energy is in cosmic ray, and the other in thermal or in kinetic or things like that. But for these like this like zeroth order study, we're testing for the cosmic ray jet, we're injecting most of the energy in cosmic ray.
So it's like not 100, but like close to 100%.
Yeah, those are close to 100%. Yeah,
But it does not ruled out in any way in any case, is it?
Yeah,
like
yeah,
it could be possible.
Yeah, so I mean, yeah, so yeah, I think it's so ideally we might want to try like a different energy composition, but yeah, that's the zeroth order thing to do for, yeah.
Sure, no, it makes sense. Thank you.
So thank you very much, Konji, for your presentation.
Thanks.
And thanks to everybody for participation at this seminar. And everybody is welcome to register for our other seminars, and encourage your colleagues to present the scientific investigations. So thank you for everybody and for presenters of today, and see you again in about a month.